So we have now seen what the search states look like in our new search space, and we have seen what the state transitions in this new search space look like. And there were 4 such transitions according to the 4 components of a partial plan. We could add an action, we could add an ordering constraint, we could add variable bindings, and we could add causal links to the partial plan. This means we're very close to the definition of plan space search as a search problem. So we will look at the missing bits and pieces next. The first thing that is missing to define our problem is the initial search state. Our initial search state is the empty plan that contains only the goal and the initial state, and we will add the goal and the initial state as dummy actions to our plan. To do this, we have one action init that has no preconditions and has everything in the initial state as effects of that dummy action. So if this is the first action in our plan, the result is that the initial state holds. And then we have another action in our plan, goal, which contains all the goal conditions as preconditions and has no effects. And if this is the last action in our plan, that means before we can execute this goal action, all the preconditions must hold, which means the goal has been achieved. Our initial search state is then the empty plan pi0 consisting of the following component. First, we have the 2 dummy actions init and goal, which we've just described. Then we have one ordering constraint, namely that init must be before goal. We have no variable bindings initially, because there will be no variables in the initial state or in the goal. They're all fully ground. And finally, there will be no causal links between any of the propositions in the initial state or the goal. That is the empty plan, the initial search state we'll be using to start our search. And here is our empty plan in a pictorial representation. We have the 2 dummy actions, init and 0. These are 2 actions in this plan. So each action consists of preconditions and effects. The preconditions of init are here, and they are of course empty. And the effects of goal are here, and again, they are empty. Otherwise, what we see are the initial propositions from our initial state in the planning problem, and the goal conditions from our planning problem. Also, we have this ordering constraint here saying that init has to come before goal. That's it, that's the empty plan. And I hope you're not getting confused with the initial search state here. So we distinguish the initial state that is part of our planning problem, which is a world state consisting of all these ground atoms, and we have the initial search state, which is the state from which we start our search, in this case a partial plan. The two have nothing to do with each other, although they are both initial states in some way. One is the initial state in the world state space, and the other is the initial state in our search. The successor function we need to define our search problem is of course given by the plan refinement operation we've seen previously. So we generate successors by applying our plan refinement operators, and we can apply one or more of these operators at the same time to constitute one step in our successor function. And the reason why we want several operators at the same time is simply that we need to keep our partial plans consistent. So we've already seen examples of that, namely when we add a causal link, we should also add an ordering constraint at the same time, in the same step. This is necessary to keep our plan consistent. So our plan refinement operators are combined to give us the successor function. We use one or more of the following: adding an action, adding an ordering constraint, adding a binding constraint, or adding a causal link to the partial plan we're currently observing. And we want to do this in such a way that our partial plan remains valid. So that means that all the constraints we add as part of our plan refinement must be satisfiable in some way. You can see that what plan space search is doing is decoupling 2 problems that we need to solve as part of planning. The first problem is which actions to execute as part of our plan. And the second problem is how to organize these actions. What is the organizational structure that underlies our plan? Another view of plan space search is that we view a partial plan as really representing a set of plans, namely all those plans that we can achieve from this partial plan by these plan refinement operations. So every time we apply a refinement operation, as part of our planning process, we reduce the set of possible plans into which the partial plan can be refined. And we do this until the plan is fully ground and there is only one plan left. Now, what remains to be defined here for our plan space search problem is the goal test. But before we define the goal test for our search problem, we need to reconsider what we understand by a solution for a given planning problem. Just a quick recap. A planning problem was defined by a state transition system, initial state, and a goal condition. And a plan pi is considered a solution for this planning problem if the application of the plan in the initial state gives us a new state, and that state satisfies our goal. That is how we've defined a solution for a planning problem. And here is the problem that we have now. This term, gamma Si pi, was only defined for a sequence of ground actions because those were the only plans we've considered so far. The plans we are considering now are only partially ordered. Of course, we can turn this partial order into a total order by respecting all the partial order constraints. But then the question is, in our definition of gamma Si pi, which of these total orderings should we use? In general, there could be an exponential number of total orderings that correspond to one partial order. Similarly, our partial plan may only contain a partial instantiation of the variables which we will need to bind in our plan. So there may be a large number of ways to turn our partially instantiated variables into a fully ground plan, and we need to decide which one of those to use for our definition of a solution. The simplest way to address this problem is to consider a new definition of a partial order solution. And here is our new definition when a partial order plan constitutes a solution to a planning problem. A planning problem, of course, consists of the same components as before, which means it's a state transition system, an initial world state, and a goal condition. And we consider a plan that may be a solution consisting of actions, ordering constraints, variable bindings, and causal links. That may be a partial order solution for our planning problem if two conditions hold. Firstly, the ordering constraints and the variable binding constraints in our partial plan must be consistent. The ordering constraints are consistent if there is no loop in the orderings, and the variable binding constraints are consistent if we can find values for all the variables such that all the constraints, which are equalities or inequalities, are respected. So, in our partial order solution, all the variable bindings and ordering constraints must be consistent, and we have another condition, namely that for every total order sequence of A1 through AK, which are the actions in A minus the init and goal actions, these were the dummy actions we've only used in our empty plan. The other actions were the ones that were added through plan refinement operations of the first type, namely adding actions. So, every such totally ordered sequence that is fully ground and respects the orderings and variable binding constraints must satisfy the following condition. That is, if we apply this total order plan in the initial state, then the state transition function gives us a new state which must satisfy our goal. So there is an exponential number of ways to turn our partial order plan into a total order plan, and our definition for a partial order solution now requires us to have every such total ordering satisfy our goal. There are a few things to note here, and the first interesting thing is that the causal links apparently don't play a role in the definition of a solution plan. The second is, if we want to turn this into a computational procedure that we can use as a goal test, it is not very practical. If we have to test every total order sequence and there is an exponential number of such sequences, then we have a lot of work to do to verify our goal test. But of course, in the construction of our plan, we pay careful attention to the way we combine the action. And in fact, if every precondition of every action is supported by a causal link, then we know that our plan will satisfy the goal, because the goal is the final step in our plan. The problem is, this condition, that every precondition is supported by a causal link, is not quite strong enough as a goal test yet. But we will get there soon enough.